Over the course of 8 years on Réunion Island, one of the most ambitious engineering feats of the 21st century took shape. A construction project unlike any other, stretching over 13 kilometers, built partly in the open sea, a hybrid road of colossal seawalls, vast interchanges, and a monumental viaduct.
A 5.4 billion euro project, unprecedented in France, with seawalls supporting a platform over 36 meters wide. It's remarkable.
This structure, rising above the waves, has been designed to withstand the test of time. It will have to endure relentless tropical cyclones and towering ocean swells.
It's awe-inspiring to picture a wave nearly as tall as the wall crashing into the riprap.
In the Indian Ocean, the challenge is immense. Every part of the island must be combed for the 83 million tons of rock, concrete, and steel needed for construction. To make it happen, exceptional logistics and heavy machinery are required. At the heart of the operation, the Zoorite barge, capable of precisely placing concrete blocks weighing around 5,000 tons.
It's a massive machine, built for an extraordinary project.
The barge is impressive, especially when it lifts itself up on all 8 legs.
It really is incredible.
Specialized vessels are also needed, capable of shaping the seabed for kilometers on end.
Pinocchio is a dredger mounted on a barge that can fill a semi-trailer with each bucket.
Everything is coordinated by teams of specialists, experts in construction, and in the extreme conditions of this environment.
If you go up against the sea, you'll always lose. So we're going with it instead. The key is to understand it.
Perfect. Here we go.
How do you build a colossal structure in the heart of the ocean? What engineering feats and design choices will allow it to withstand the forces of nature? And how do you ensure it stands strong for generations to come? Architects, engineers, and builders will take on all these challenges and work together towards a single goal: to create the impossible, a road that defies the ocean itself. In the heart of the Indian Ocean lies Réunion Island, a natural jewel shaped by the elements. Located on continental Africa, over 700 kilometers from Madagascar, this volcanic island spans roughly 75 by 55 kilometers. Its landscape is dominated by a mountain range soaring nearly 3,000 meters, the highest in the Indian Ocean. Two giants define Réunion's terrain, the Piton de la Fournaise and the Piton des Neiges. Together, they shape not only the island's topography, but also the character of its people and their way of life. Here, most activity is concentrated on the coast. 3/4 of the population live within dozens of kilometers of the seaboard. To get around this thin strip of land, cars are by far the main mode of transportation. Over time, the National Highways 1 and 2 have developed around the island. But even avoiding the highest mountains, crossing the island is no easy task. The road must cross mountains, lava fields, deep ravines, and sometimes torrential rivers, all while protecting against rocks falling from cliffs. It's a real obstacle course. For decades, the people of the Réunion have carefully crafted this network of roads in close harmony with nature. Beyond protective measures, they have built remarkable works of art capable of traversing the landscapes.
These volcanoes, this location in the heart of the Indian Ocean, and these extreme climatic conditions mean that building infrastructure here on this island always leads to exceptional works. When you travel around the island, it's amazing to see these works, which are both a challenge and an illustration of mankind's ingenuity, our ability to overcome obstacles.
The majestic Route des Tamarins, with its extravagant viaducts, is a perfect example of Réunionnese road engineering. Constructed in the 2000s, its 4 lanes across deep ravines and highlands have changed the lives of residents in the west of the island. The route de Tamaran was a success, and now focus is turned to the northwest of the island, the road between Saint Denis and La Possession. Administration, tourism, industry, and harbor activity. These two urban areas bring together the island's essential activities and ever-increasing road traffic. To connect both cities, a 4-lane road has been mapped on the coast along a cliff face. The famous Route du Littoral coastal road. It's a stretch of National Highway 1, used by almost 80,000 vehicles every day.
The coastal road links the harbor and airport, connecting two important economic areas, the northwest and the north. In the northwest, you'll find the harbor, beaches, and bustling tourist and industrial areas. The north serves as the administrative center and technology hub. This vital connection must withstand whatever conditions come its way.
This road, as strategic as it is essential, faces constant challenges. Squeezed between the ocean and the cliffs, it's constantly at the mercy of the elements. Frequent cyclones bring winds exceeding 100 kilometers per hour and torrential rains powerful enough to dislodge deadly boulders from the rock face. At the same time, swells over 30 feet high crash over the road, flooding and blocking it off. To prevent disaster, protective nets have been installed along the cliffs to catch falling rocks before they reach the roadway. The sides of the roads that have been worn away by waves are continuously being rebuilt, and a clever lane-changing system has been put in place to protect vehicles from both rockfalls and swells. As essential as this is, it entails high maintenance costs and increasingly complex traffic challenges.
The journey in regular weather conditions takes 15 minutes, but when there's a diversion, it can stretch to an hour. There's a stream of people who live in the west and commute to Saint Denis, then go home in the evening. So road closures and traffic restrictions cause major disruptions for many.
The situation is becoming almost untenable for daily road users, especially since, despite all precautions, tragedy struck. On the morning of March 24, 2006, an entire cliff face gave way, claiming 2 lives. It became imperative to rethink this road so crucial to the island. So the decision was made to construct a new coastal road. While the starting and ending points remain unchanged, numerous projects and strategies are being explored to improve this particularly critical section.
The goal now is to stop fighting the elements. It's been done for decades, with mixed results at best. In the end, it's a losing battle. You can't fight the ocean. The idea was to move away from the cliff, to work with nature rather than against it.
Surprisingly, the best solution to ensure safety and protect against geological and maritime hazards is precisely to go via the sea, to stay away from the cliff while overlooking the swell.
The new coastal road had to be completely free from rockfall. The very first task to be carried out was to complete a study of the cliff, to calculate each time a rock fell from the cliff, where it would fall, and whether it would bounce, and so on. This allowed for the creation of what is called the rockfall polygon. That is to say, the line beyond which no block should reach, and it was decided to create the entire road beyond this polygon. On the other hand, we tried to stay as close as possible to the coast, because the further you go out to sea, the deeper it gets. That's how the road took the shape it has today, conformed in parallel to the current cliff, to avoid those depths.
The new coastal road stretches out to sea, intricately following the coastline for 12.5 kilometers. Neither too close nor too far from the shore. To make this vision a reality, Engineers and architects designed a road composed of a series of enormous, interconnected, and complementary structures. From Saint-Denis, the structure takes the form of a huge 1,460-meter-long seawall, firmly anchored in the ocean floor. This structure serves as an anchor point for an enormous viaduct that's over 5.4 kilometers long. The coastal viaduct. The road continues over a series of smaller seawalls and viaducts, less massive yet equally complex, designed to serve the town of La Grande Chaloupe and maintain the cohesion of the entire structure. After just 12 kilometers, this monumental road finally reaches its destination, the town of La Possession. Despite its hybrid design, the new coastal road stays true to its purpose, ensuring the safety of every user down to the smallest risk. The viaducts soar 20 meters above the water, allowing even the highest waves to pass beneath. Set between 160 and 1,000 feet from the shore, they are well beyond the radius of cliffside rockfalls. The massive seawalls that connect these towering structures to the mainland are not to be overlooked. Also, far from cliffside hazards, these seawalls are equipped with anti-cyclone and anti-submersion systems to withstand the most extreme weather conditions. To bring this ambitious project to life, multiple large-scale construction sites, spanning kilometers both on land and at sea, were launched in a coordinated effort.
This road is a truly colossal undertaking that began over a decade ago, involving hundreds, if not thousands, of people who researched, designed, and engineered a route capable of withstanding the force of the sea and the cyclonic swells. It's a beautiful project, the likes of which you rarely see.
The first phase took place in 2014. By 2015, work was underway on the most iconic structure of this massive undertaking. The coastal viaduct, stretching its 5,400 meters. It's the longest bridge ever built in France. The shape of this extraordinary structure was carefully refined over many months. Designed to stand proudly before the cliffs, it is destined to be a symbol of the island.
When you arrive in Réunion, the plane flies right in front of the new coastal road, so every visitor gets a glimpse of it. That makes its integration into the landscape a true architectural challenge. How can this road harmonize with the dramatic mountainous backdrop behind it?
To avoid overwhelming the foreground of the landscape with a massive structure, a sleek, slender design made up of arches was chosen. The number of piers, those supports anchored to the seabed, was also kept to an absolute minimum. It's a way to give the structure an almost weightless aerial quality, while also minimizing its impact on marine life. Fittingly, construction begins with these very piers. The viaduct's foundations must be securely anchored to the ocean floor. In total, 48 piers must be laid down to the nearest centimeter. The first step is to prepare the areas where these supports will be installed, a process known as leveling. It's a logical, standard procedure, with one major twist. Here, it all takes place underwater. To pull off such a feat, the construction teams relied on a machine as unusual as it is impressive, nicknamed Pinocchio.
Pinocchio is a dredger on a barge, capable of filling a semi-truck with each bucket. Its job was to prepare all the seabed so we could move forward with the project. Wherever Pinocchio passed through, it meant we were ready to get to work in that area.
Pinocchio is nothing less than the most powerful aquatic excavator in the world. 4,000 tons of steel and ingenuity. To dig and reshape the seabed, this barge is equipped with a 550-ton dredger. At its end, the bucket can remove 14 cubic meters of rock from beneath dozens of meters of water, all with a single joystick command. Despite its enormous scale, Pinocchio also needs to operate with pinpoint precision to counter the motion of the ocean. 3 massive stakes plunge to the bottom of the seafloor and lift it a meter above the water, giving it the required stability. Pinocchio is now ready to carve out the terrain that will support the viaduct's foundations. Before construction began, a geological study was able to precisely analyze the soil's composition. The goal was to locate a healthy, solid rock layer strong enough to support the structure's foundations, what engineers call ground support. In light of these analyses, Pinocchio excavates 3 to 8 meters deep into the seabed to reach the right layer of rock. Once that stable point is found, a 400 square meter circle is marked out, excavated, and leveled to perfection. A bed of ground rocks is then deposited to reinforce the terrain's resistance and stability. Now, the seabed is ready to accommodate the pier and support the forces of the structure. It will take Pinocchio several months to prepare the ground along the full length of this emblematic viaduct. By the end of 2016, the site was finally ready to lay down the first foundations. To support this colossal structure, over 5 kilometers long, 48 piers will be needed, each one 120 meters tall. These concrete giants will carry the entire weight of the viaduct and its roadway traffic.
The structure itself, with its 48 underwater piers, was the focus of meticulous design and small-scale models, where swells and waves could be generated to study the support's stability and their impact on the ocean.
In the end, a very specific foundation system was chosen. The piers will simply be placed on the seabed. To ensure the viaduct's stability, the piers are round, allowing ocean currents to pass through rather than resist them. But they're also incredibly massive, each weighing over 7,000 tons, capable of sitting securely on the ocean floor. This non-invasive technique minimizes environmental impact while also streamlining the industrial production of these steel giants. Southwest of the construction site near Le Port and La Position, a dedicated plant was built to manufacture all 48 support piers. This factory operates in a continuous flow, producing these massive concrete components made of 2 parts. The base, featuring an enormous 23-meter diameter, 4-meter thick footing, forms the foundation of the pier. That's 4,500 tons to place on the ocean floor. Rising about 15 meters high, the base plate is elongated with a second piece, the pier head. Its height varies between 9 and 21 meters to keep the road deck over 20 meters above water, safe from the swells. These parts, manufactured around a dozen kilometers from the worksite, must provide continuous support.
There are 2 parallel production lines for the bases and the pier heads. This setup, combined with an air cushion rail system, allows the precast elements to move seamlessly toward the loading dock.
Each pier part will then be brought to an exceptional vessel called Zourite.
Zourite is definitely Réunion's most impressive tool.
Working day and night, it's among the most important maritime resources we've used.
It's a really impressive barge, especially when it's raised on all 8 legs.
It's incredible, for sure.
This one-of-a-kind lifting platform was specially designed for this extraordinary project. As large as a soccer field, It features a mobile concrete plant and a 33-meter gantry capable of lifting components weighing up to 4,800 tons. To work with precision in the ocean, Zoorite, Creole for octopus, deploys its 8 steel legs onto the seabed. These legs can lift 32,000 tons, raising the entire platform and its load several meters above the water. Now anchored in the ocean, Zoorite is in position to begin installing the first structural bases. Naturally, the process begins with the base plate, which will ensure a firm grip on the ocean floor. Using its powerful gantry, Zoorite lifts the 4,800-ton piece of concrete and positions it above the water. Meticulous steering, assisted by divers and guided by a geolocation system, allows it to precisely take the base plate of the pier down into the depths. Once on the ocean floor, actuators fine-tune its position, lifting it slightly by 40 centimeters. Then a new operation begins. The onboard plant starts up, and a thin cement mix is injected into huge sacks below the base plate to refine the contact between the underside and the bed of ground rock.
Once these materials are injected, the actuators gradually release pressure to ensure that the weight of the base plate crushes the sacks of concrete, ensuring a perfect bond between the base and its foundation.
Underwater, divers follow Zoorite's every move and continuously monitor the progress of the operation.
We witnessed the entire installation of these bridge piers, 48 in total. Each one required multiple inspections and precise measurements. You have to pay attention to pumping, filling, any potential leaks, routine maintenance operations, as well as the disassembly of the various systems involved in the pier laying workshop. So the work was incredibly detailed, down to the last centimeter.
The divers act as the surface team's eyes underwater. The smallest misalignment on just one pier could jeopardize the entire project. Once the base plate is correctly positioned, Zoorite can finally start putting the upper part in place. The pier heads is the part that allows the viaduct to rise above the sea and its swells. Each part fits into another, held together by an injection of reinforced concrete. Underwater, one last process must take place. Laying down a 400 square meter concrete mat, designed to protect the underside of each pier from the forces of nature.
We've just laid down what are known as anti-scour mats, a series of concrete blocks in a 20-meter radius around the pier. In case strong swells or currents attack the foot of the pier, this prevents the level from going down.
It can happen that during storms or other phenomena, swells get a bit more aggressive, and so can lift the sand up at the bottom of the structures. So the foundations must be built to withstand those natural forces that cause erosion.
By flattening the sand under these concrete blocks, each pier base is protected from erosion. After 4 years of construction, on March 15, 2019, all 48 piers were finally in position, securely anchored to the seabed. Meanwhile, designs for the rest of the structure had begun, and the coastal viaduct was taking shape. To bring the viaduct to life, both prefabrication plants, built especially for the project and a stone's throw away, need to be kept running at full capacity. The concrete ballet has just begun. The first factory was designed to manufacture 48 piers. The second, which is larger in scale, must produce all 1,386 voussoirs, which once built will form the deck, the horizontal part of the viaduct which carries the road.
These prefabrication facilities are substantial in size. The voussoir factory covers over 10 hectares. You need lots of space for the iron framework, manufacturing the steel and the massive molds, and storage areas.
The frames of the voussoirs are first steeled with rebars, then poured into huge concrete molds. As the arch-shaped deck is irregular, the dimensions of the molds are adapted using a system of hydraulic actuators. The voussoirs then take on different shapes. For 24 hours, a massive gantry moves these 300-ton pieces for storage before transportation to the worksite. Beyond this highly synchronized system, special attention is paid to the concrete mix. A total of 300,000 cubic meters of concrete will be used for the 5,400-meter-long viaduct, enough to fill 100 Olympic swimming pools.
One of the biggest concerns was the quality of the concrete. It's a well-known product, but very specific studies were carried out to make sure its composition was adapted to durability. So that was really one of the biggest issues in this project in terms of materials.
The structure must be able to last at least 100 years without needing any substantial maintenance. The concrete used mustn't be too porous to prevent ocean spray and sea salt from penetrating the structure. This requirement calls for the mixture to be kept relatively cool during processing, a real challenge in the tropical climate of Réunion Island.
This project used considerable volumes of concrete, and concrete tends to overheat. So, an extremely sophisticated system was required to prevent the concrete from overheating. It went as far as adding ice to the concrete formula in summer to maintain an acceptable temperature and improve durability.
45 tons of ice are produced each day at the worksite and incorporated into the mix to maintain an acceptable temperature.
Concrete has become a real science. It needs to fit our exact specifications while retaining the all-important operating speed. We need to keep an industrial pace, casting segments one day, unmolding the next, so it can go straight to the loading bay, where the cells are ready underneath to remold new voussoirs.
In this way, the factory is able to produce 3 or 4 pieces per day. In 2 weeks, that's almost 120 meters of viaduct ready for the worksite. But some voussoirs require special treatment. These are mega voussoirs, which will be placed atop each pier.
At the top of the piers, the voussoirs are much bigger and much higher. We call them megavoussoirs around here because they're around 7 meters long. They're extremely big, heavy components.
These giant pieces are made from several prefabricated parts that must fit together with absolute precision, like an extra-large 2,400-ton building set. These mega voussoirs are then transported to the harbor using an air-cushioned rail system. And once again, the mighty Zoorite lifts and installs them with millimeter accuracy at the top of each pillar. An operation executed with centimeter-level precision. It's now these huge pieces of concrete that the rest of the structure will lean on. To finish building the viaduct, the gaps must be filled in. About 30 standard segments are placed between each pair of pillars. In total, 1,386 segments will be delivered from the prefabrication plant to the site.
These voussoirs, which are particularly heavy, were also transported on land on what are known as flatbeds. These are specific machines with several dozen axle trees and wheels, built to carry extreme loads.
These 35-meter-long, 100-ton trucks had no choice but to use the old coastal road to reach the end of the viaduct under construction. Therefore, every night, traffic is diverted and an unusual convoy is organized. At their destination, a new tool prepares to take over the voussoirs, a bridge layer.
Once the voussoirs were transported to the site, they were brought to the foot of the bridge layer. This is a metal structure a little over 300 meters tall, around the same height as the Eiffel Tower, that's supported by 3 piers.
Securely on its supports, the 278-meter-long bridge layer only works on the central pier. It picks up a pair of voussoirs and positions them on either side of the pier to maintain balance. The voussoirs slot together and are provisionally fixed in place with a specific adhesive and an actuator system before another pair is added. Little by little, the bridge layer fills the gap between each pier and forms something known as a span. Each month, 2 spans are completed, and the bridge layer can move on to the next piers. One final operation is essential to ensure the structure's strength: the addition of pre-stressed PC strands, cables that stretch at regular intervals across the structure, compressing the voussoirs together.
Basically, pre-stressing is the principle behind a stack of books. If you want to carry a stack of books horizontally, and you squeeze both sides of the stack, you should be able to transport them without the books in the middle falling. So pre-stressing means exerting pressure to maintain resistance.
These are the PC strand sheaths on the deck for abutment C0.
By keeping the voussoirs tightly compressed, the PC strand system reinforces the entire structure and guarantees it will remain stable. Inside the deck, a gallery stretches along its entire length to house the technical networks, essential for ongoing structural monitoring and for connecting the viaduct to various information systems.
An internet network has been installed, with terabytes of data passing through the new coastal road from Saint-Denis to La Possession.
Rainfall, wind monitoring, traffic density. All this information will help ensure the safety of road users during extreme weather conditions. In February 2021, after 7 years of construction, the viaduct structure was finally complete. At 5.4 kilometers long, it's now the largest bridge in France. On the surface, the roadway was laid and asphalted, ready to carry traffic. However, the new coastal road isn't finished yet. The viaduct accounts for only 5,400 of the 12,500 meters needed to connect Saint-Denis to La Possession. A smaller scale bridge is also being built at the halfway point near La Grande Chaloupe, and another is planned to complete the route to La Possession. Each of these structures is anchored to huge seawalls, ensuring the integrity of the whole system. These giants of stone and concrete stretch for a total of 4 kilometers and are among the most massive civil engineering feats ever attempted. A fortress of concrete capable of withstanding the elements for 100 years. Construction started at the same time as work began on the new road. It's a mammoth task. It needs to rise high enough above the water to keep traffic safe, while resisting the sea's relentless force.
It's awe-inspiring to imagine A wave coming in
The height of the wall.
that's practically the same height as the wall and breaking against the riprap.
So these seawalls must also be based on an ironclad design. They are mainly comprised of a body extending from the ocean floor and rising gradually by means of a riprap, made from increasingly big and heavy materials. The material varies from small stones in the core of the structure to several tons on the outside. A final layer made from concrete blocks weighing several dozen tons forms an armor around the seawall. The principle is simple. A wave hits the biggest blocks and then seeps through the gaps. The water then runs into more blocks, which are smaller but tighter, and so it goes on.
It keeps alternating between the material and the gaps. So when the swell comes, part of it will break against the material and the other part will go into the gaps. The varying impact with material and gaps as it hits the seawall dissipates the energy. It's like being broken up little by little.
With the swell broken, the seawall rises further to support the road above. It is protected by a reinforced concrete seawall along its entire length, and equipped with a wave deflector to drive back any waves that have found a way in. Elevated some 20 meters above sea level, the road is safe from flooding. To calculate the dimensions of this project, the engineers must consider the island's unique features and simulate the most extreme scenarios. They test different options and configurations on highly detailed scale models, even accounting for future sea level rise.
All the seawalls of the last 20 to 25 years are analyzed, and projections are made for the next 100 years. What's the biggest swell that could come in? This swell is then tested on a scale model of the project, where we recreate in miniature the seabed and the waves that will crash against the structures, so we can check the whole preliminary design works well.
The seawalls are designed to withstand regular waves of 13 meters and peaks up to 26 meters. With the design finalized, construction begins. Once again, work starts by preparing the terrain with the help of the famous Pinocchio barge.
Pinocchio's job was to construct what's known as the foot of the seawall, a big underwater trench to remove the sand and then, during the construction phase, substitute it with ripraps. So, a more solid, stable, and durable foundation.
Once the foot of the seawall is complete, construction now relies on an enormous supply of materials. 9 million tons of ballast and riprap. The first part is transported by sea using a huge side-loading ship, capable of precisely delivering its load all along the work in progress. Next, it's the land team's turn to take the reins. A never-ending procession of trucks delivers cargo to the worksite, while bulldozers push these materials into the water for the seawall's construction. Together, these teams methodically build the embankment, overlaying bigger and bigger rocks. But this meticulous process depends on a continuous supply of materials, and that's where a major challenge arises. The island's quarry workers are unable to build the biggest ripraps. So the construction teams turns to one of Reunion's distinctive features. For decades, farmers here have had to remove blocks of stone from their fields to work the land. They then move them to the edge of their fields, forming what are called windrows.
The idea was to send the machines to the fields to collect rocks, which would, on one hand, help the farmers recover arable land, and on the other hand, gather the scarce resources for the upper riprap, which was the hardest to construct of the quarries. We could gather a great deal, store them, sort them, and bring them back here to the work site to use in the seawalls.
Around 200 acres of agricultural land were salvaged in an area with a tendency to lose arable land. That was a win for both local farmers and agricultural production on the island. It supplied 4.4 million of the 12 million tons of riprap needed to build the seawalls.
Back at sea, construction can continue. The slope of the seawall extends 11 meters below the surface and rises 5 meters above it. It's a matter of arranging everything to perfection. Excavators equipped with arms bigger than 30 meters work in the deep with precision, guaranteeing the future structure's durability. The last step is to position the outermost layer of the seawall. This frontline barricade faces the sea, designed to absorb nearly all of the swell's energy. This armor is made of enormous blocks with very particular shapes. For good reason. They are not quarried by nature, but custom engineered for the task.
While building the seawalls, we start with the smallest ripraps and then move to the larger and larger ripraps. But a moment comes when we switch to concrete, which is a denser and heavier material. Above all, we can be sure to use layered technology. That combination of weight and interlocking provides superior resistance to waves and all kinds of external stress.
The acropode is one of many ways to protect seawalls. It's a large concrete block which was developed to respond to certain requirements, which are durability, resistance to swells, and permeability to break the swells while remaining steadfast. Everything is fitted together to resist swells.
These acropodes, concrete blocks weighing around 30 tons, must be positioned accurately to fit into each other, while leaving space between them to allow some of the wave to filter through after its energy has dissipated.
It seems simple, but it isn't at all. Each block is set at a different angle. They need to face different ways, and, above all, they need to have contact with the bottom layer of the riprap. 3 points of contact between the riprap and the acropode are necessary to ensure imbrication. What we want to avoid is a block coming loose in the event of a swell.
The acropodes are installed using a 300-ton crane equipped with a 55-meter-long arm. A precise installation plan is followed. Each block is numbered and geolocalized. Positions are calculated down to the inch. This armor must be flawless. It's a delicate job that, again, relies on support from dive teams.
Today we're going to position the acropode. We have some bad weather conditions at the moment. If the waves don't let us, we won't take risks, okay?
That works for us.
Perfect.
Here we go.
We were on site to supervise the installation, to keep an eye on how the acropodes were going to fit together. All it takes is one defect in the embankment to have a direct impact on the armor, so there are adjustments to make. You can't verify those adjustments on a blueprint, so it's the diver who at that moment can say, we have this or that problem, we have this or that constraint. That's how we can respond to it.
In total, 23,000 acropods are installed along the new coastal road seawalls. Together, they form an unshakable barrier. To stay safe from the ocean's wrath, the road must rise to a minimum of 15 meters above sea level. It is then protected by one last shield, the sea-chasing wall. An insurmountable reinforced concrete wall. This barricade will support the road while resisting even the strongest waves that make it past the acropodes.
There are two steps. The first step involves the acropode dissipating most of the energy. The second step is the water that's left, which has managed to get through, breaks against the wall, and goes into the ripraps below.
This 90-centimeter thick wall is reinforced along its entire length by stiffeners weighing 60 tons. They give the structure all its sturdiness. At the top, a curved wave deflector is installed, capable of sending the fastest waves back out to sea. Once the wave-chasing wall is complete, the seawall is ready for the road to be paved. By the end of 2022, 4 seawalls and 2 viaducts, totaling 10 kilometers long in total, have taken shape, securely anchored in the ocean. The final step of the project in the years to come will be one last viaduct, 2.5 kilometers long, linking the route all the way to La Posesión. But traffic is already circulating on this first portion of the new coastal road. Drivers travel between Saint-Denis and La Grande Chaloupe, safe from the dangers of the cliff and the ferocity of the waves.
Let's take a quick look at the new coastal roads viaduct. Traffic is currently flowing calmly with few incidents. On that good note, we'll check in later to see how things are going.
Providing access to the new road are recently added structures that extend from land to sea, interchanges. These complex constructions have several responsibilities. They must ensure safe access while taking into account the joining of various flows of traffic. But they are also the face of the project. They are the most visible part of the structure seen from cities, as well as being the first view for arrivals.
At each end, Saint-Denis and La Posesión, there was an interchange to organize, a connection to add to the existing road network. We really wanted to take care of this monumental project. After weaving through the sea for 12 kilometers, each end had to be very carefully thought out.
In La Posesión, on the western end, work has already begun on a symbolic interchange, while waiting for construction of the final segment. To connect the last maritime structure to land, another seawall, over 400 meters long, has been built. With this, the bridges have become layered. A web of traffic lanes gives the whole thing a feeling of lightness, with the ocean peeking between the lines.
The interchange at La Posesión is a little atypical, being built on 3 levels. At the top is the coastal road. Below, there's a small ringed intersection which allows the exits to serve all of La Posesión. And even lower, there's a route over a ravine. So there are 3 levels, with a particular emphasis on the ravine and the passage of water, adhering to our goal of letting natural elements pass through and not blocking them.
Following 8 years of construction, after mobilizing thousands of people and using more than 83 million tons of materials, the new coastal road finally emerges from the sea. It required rigorous and complex planning, exceptional methods and tools, and constant adaptation to the elements.
If you go up against the sea, you always lose. So we work with it, understand it, and adapt our structures to it, including positioning, choosing areas that are less exposed, or technologies that will dissipate energy. But clearly, the sea will always triumph. So we're collaborating with it instead. The key is to understand it.
Thanks to deep knowledge of the complex terrain, respect for the precious and unpredictable environment, and above all, the expertise of engineers, laborers, and architects, the project is a success.
There's a sense of pride in completing one of France's biggest maritime projects.
It's a wonderful human venture. I think a lot of people who worked on it can be proud of their contribution. I think it's an elegant structure.
The slender viaduct above the sea, following the coastline, it's a beautiful project.
Today, the first section of the new coastal road stands strong above the ocean. It fulfills its function as a strategic and safe road while blending into the seascape.
We rescheduled, we postponed, we took a step back, and we gave it a maritime nature. It's an exploration of Réunion Island's insularity.
The project isn't finished yet. In a few years, it will finally connect to La Possession. It promises to become a true symbol of the island. A remarkable and demanding construction, pushing engineers to new heights, leaving a lasting mark on the future of civil construction.